Hello, this is T Chapman 500. Welcome back to Logisim Evolution. This is an expanded version of Ben Eater's CPU. I've wired the program counter so that it can output directly to the RAM address. And I've made it so that the address register can also output to the RAM address. And I've added a multiplexer to select between the two. We no longer have to wait an extra clock cycle for the program counter to be loaded into the address register. So there's one of the optimizations I made. Also, these are full 8-bit addresses. So we have a full 256 bytes of RAM. We now have 8-bit instructions. And I have a somewhat inaccurate signal reference here. I've added a few more signals. By the way, I've also updated the instruction set to be more compatible with Ben Eater's instructions. Although, you can hardly call an 8-bit instruction compatible with a 4-bit instruction. Anyways, the signal labeled AS will set the address register into the address input of the RAM. The SR will reset the stepper. In here, I have a little input that resets the stepper synchronously with the clock. So when this is active, on the next clock pulse, a 0 will be loaded into the stepper. Now, I don't have all of the instructions working with this particular improvement yet, but I will soon enough. Let me save off the changes first. I am going to load up, actually I've already loaded up my first attempt to build a CPU before I saw all of Ben Eater's videos, well, most of Ben Eater's videos. Now we are in the original Logisim by Carl Birch. I hope I pronounced that correctly. And this is just the reset and RAM reset. I've separated those two so that I can reset the CPU without having to reprogram it. Anyways, I based this CPU off of something I saw in a No One Lesson video. I'll link to those relevant videos in the description. In those videos, they show what's inside a CPU and don't really talk about signal control the way Ben Eater did. And the way they did explain some of the signal control was to imply that the clock input was to be put high when you were ready to write data into the register, which kind of led to a few things. So if I go into the control unit, the device labeled MAR tasks, this is the solution I came up with to prevent a signal from going high incorrectly. Basically, put it in a flip-flop. When it's ready to go high, it will go high once. When it's ready to go low, it will go low once. I must say, I like Ben Eater's method of using the enable wires a lot better, because the enable wire will simply disable the clock until you're ready to write data to the register, which means these T flip-flops aren't necessary. So if we go back out to the CPU core, oh, I forgot, one of the features, we can go to the execution tree, go into the command unit, come on, and then go into the decoder. I basically have one D flip-flop here for every possible instruction combination, which is going to prove to be inefficient on the simulation side. Also, if we go back to the command unit, actually no, the core, expand this out slightly. The memory address register. Originally, there was a return register somewhere over here that I replaced with a stack. Where's the stack? Here it is. Now, when the call instruction was executed, the stack would be incremented, then what was in the program counter, or what was in the program counter plus a certain value to be the return address, would be loaded into the address, in theory. Then when a return instruction was executed, the address that was at the current stack location would be loaded back into the memory address register, which was acting as the program counter. And then the stack address would be decremented, going to the previous address. That's what broke the CPU. Now if we go back to the CPU core, we can see the instruction address register, which would be loaded if there was a jump or call instruction, and a jump instruction would load the address into the memory address register. Call instructions would also load what was in the instruction address register into the memory address register, and then a load or store instruction was supposed to load what was in the instruction address register directly into the RAM. That didn't work out. Previously, it would just load the instruction address register, then load the results into the memory address register, set the return address, then load the return address when we were done with loading and storing data. But this, what I thought would be a small change in the architecture, turned out to be a CPU breaking change. It no longer works for any of the instructions, at least not that I can tell. So this is what I came up with before I saw most of Ben Eater's videos. And definitely before I saw Ben Eater's video on signal control. Very helpful, by the way, thank you. And let me show you the arithmetic logic unit. I have 15 operations that can be performed by this arithmetic logic unit, and divide is not one of them. I can add, subtract, negate, increment, decrement, multiply, do all 7 of the logical operations, do shift operations, and compare. But I cannot divide. At least there's no hardware implemented divide. This is what's left over from my attempt to build an 8-bit CPU without watching Ben Eater's videos. Now, some of the modifications I have made since then would be to tie the enable wire for this multiplexer to high, and tie this controlled buffer's control input to ground, as well as tie the multiplexer to ground. And that was just a desperate attempt to see if the original instructions still worked, which they didn't. None of the instructions, as far as I can tell, work. So now I have a few options. I've already zipped up this CPU in a zip file. I could probably post it somewhere like Google Drive and post a link to it and allow you guys to see if you can fix the CPU. I can also try to fix the CPU myself if you would like, or I can just leave it as is, and I'll bring up my second attempt to show you what I did because of this breaking of the CPU. So here's the control unit that I've built. Well, part of it anyways. I haven't completed it yet, but this is what I decided to do to my original CPU design after I saw the relevant videos by Ben Eater explaining signals and signal control. So, like in the last video, we have different fields. The instruction class basically has just 1 bit to it, and if the class is a 0, then it's not used by the arithmetic logic unit. If it's a 1, then it is used by the arithmetic logic unit. We also have the register, that is the A input. So the register is for the A input, and instructions that don't use this register field, well, they may use the register field for something else. And as you can see here, I do not have a single T flip-flop controlling these signals. Actually, I'm going to remove this one, this controlled buffer, replace it with an OR gate. Because I can't really use a controlled buffer here, it will probably short out the CPU lines. But I can use controlled buffers here, I think. So this is my attempt to recreate the original CPU. Let's see, go into the stepper. After the CPU is reset, this thing will prevent execution until the clock goes high. And the clock counter, if we go here, counts all the way up to 7 before resetting. And as we saw here, we can arbitrarily reset the clock counter to speed up processing. Let's see. Oh, this part is still based on the old format of using the clock signals instead of the enable wire. And I built this using the original Logisim evolution. If we were to select this, there we go. There we go. That shouldn't be it like that. There. This is what the component originally looked like when I was still using the clock to control the set wires. So instead of using the enable and then writing the data on the next clock cycle, I would use the clock wire directly as the set wire, and that's what all these flip-flops are for. But I have not used this component. Actually, I'll just delete it. So now the reset wire is going to be on a single line. So that's to make the design a bit more compact. In the last video you saw all those OR gates that were really taking up space. I'll actually show you that. And here is what's going on now. The OR gate has been replaced by controlled buffers. The controlled buffers are inside these things. When the enable wire is on, all the controlled buffers are activated. And right now, only the no-op instructions buffers are activated. And the only OR gate is with this AND gate. That's just to make sure that we don't short anything out. I tried it with a controlled buffer, and that created a short circuit. Much more compact, much easier to tell what everything does. And once I expand all the signals, this OR gate will at least be here. I'll move it there now. And these pull down resistors just make sure that there's no loose signals activating any registers, although I don't have to worry about that on Logisim. I would have to worry about it in real life, because if more than half of the controlled buffers are trying to output a high signal at the same time that they are all outputting a high impedance signal, then the enables on the registers will register as a logic high, and that would erroneously write data to the register when the clock pulse went through, and that would be bad. So this is the second attempt at my 8-bit CPU, and depending on how you vote, I may or may not release the original design that's now broken because I didn't properly understand signal control, or I'll probably fix the original design. It might actually be easier for me to fix the original design, but I'll let you guys decide that, and it's also a good opportunity for me to test out those new cards that YouTube provides. I guess I'll finish programming the instructions to the expanded Ben Eater CPU, and then I will run Fibonacci on the new system. Okay, I got this thing programmed with Fibonacci, at least I'm hoping it's Fibonacci, so I'm going to enable the clock now. Fibonacci works. the instructions are implemented to satisfaction, at least as far as I'm concerned. This is a full 8-bit address, 256 locations, although I don't really know how you would manage to use all 256 locations yet. I'm hoping to be able to expand this a bit more in the future, perhaps with some shift operators. So yeah, we'll see how that goes, maybe in a future video. Also, I'm really not wanting this channel to be exclusively on CPU designs, so I'm going to be uploading some other stuff that has to do with other topics. It's probably gonna stay within the realm of engineering and science, though don't count on it. So you're probably gonna have to wait a little while before I upload another CPU design video like the last two. Anyways, I hope you enjoyed. This is T Chapman 500 signing off.